All right, students, welcome back to class. This today we are going to be looking into ionic theory. This topic is going to help us understand everything that has to do with electrolysis as well as electrochemical cell, which that is electrochemistry. Now, at the end of this class, or before, or by the end of this class, you as student, you should be able to state the ionic theory, and then you should be able to predict or understand what happens to you should be able to understand what happens when you dissolve your salt in water, which is sodium chloride or any other ionizable substance in water, or when it is molten, that is melted. What happens to a substance when it is melted or dissolved in water? So by the end of this class, you'll be able to tell that. Also, answer questions as regards ionic theory. So let's go into it gradually. Now, the ionic theory. Now, according to Arrhenius in 1887, explained the theory. He proposed that when an electrolyte is melted or dissolved in water, some of the molecules of the substance dissociate into freely moving charged particles, and those particles are called ions. For example, if you dissolve your salt in water, which is sodium chloride, in water, or when it is melted into liquid form, it's going to exist as sodium chloride and sodium ion, which is Na plus, and chloride ion, which is Cl minus. That means if you dissolve a compound, the compound in water, which means if you dissolve a handful of salt in water, one particle of the salt is a molecule of that salt. It breaks down into the ions, individual ions. That's what Arrhenius is telling us, and that these ions are going to be moving zigzag. They're going to be moving in a random motion. That means they're going to be exhibiting random motion in the liquid. Then, of course, the process of this dissociation is what is called ionization. The process where this salt breaks down into its ions, or a substance breaks down into its ions, is known as ionization. I would like you to underline that. Ionization. Okay, now, this is what Arrhenius is trying to make us understand. This is when you dissolve salt in water. The metal aspect of the salts, which is the positive aspect of the salts, and the negative aspect of the salts, which are the ions in this case, are going to be exhibiting a kind of motion called Brownian motion, which means they're going to be moving zigzag only. Okay, let's say they're going to be having zigzag motion, okay, or exhibiting zigzag motion. Now, imagine I dissolve salt in water. Now, let's explain what happens to. Let's use two pictures of salt, two molecules of salt actually. Now, two molecules of salt breaks down to form 4 ions, where 2 are positively charged and 2 are negatively charged, and of course they're going to be exhibiting Brownian motion. That means if you dissolve salt in water, it breaks down into its individual ions, and they exhibit this random motion inside the liquid. I'm only showing you a picture of 2, but when you dissolve a handful of salt in water, we have up to about a septillion particles moving in Brownian motion. So you can imagine how it will look like. Whatever happens to one happens to every other salt in water, as long as it's is a strong electrolyte. All right. Now, but when an electric current is passed through the electrolyte, the free ions that were moving in Brownian motion starts. For example, the positive ion will start migrating to the rod that is connected to the negative side of the battery. The rod that is connected to the negative side of the battery is called the cathode, while the rod that is connected to the positive side of the battery is called the positive side of the battery is called the anode. So take note of that. So the positive ions goes to the cathode, while negative ions go to the anode. Now, for example, if you observe what's happening in this picture here, you discover that all the positive particles are migrating to this rod. they are migrating to this rod because this rod is the rod connected to the negative side of the battery. Please, in electrolysis, the shorter line represents the negative, while the longer line represents the positive part of the battery. So that is what it means. So which means all the positive particle migrates here, all the negative particles migrates here. So at the anode, at the end of the day. So this is what happens when you dip two rods inside the solution, and then yes, let's see if we have a better animation of it. Okay, yes. Of course, this is a solution that has salt in it, and when you dissolve salt in water, it exists at its individual ions moving in Brownian motion. Now, what happens when I bring two rods in it and then connect those two rods to the battery, such that this is the positive? Of course, we have the positive side of the battery and the negative side of the battery. Now, immediately you make this connection, something is going to be happening in the liquid. What happens is that all the positive particle, what's going to happen? Remember, this is the negative rod, this is the positive rod. What's going to happen is that all the positive particle will start migrating to the negative rod, which is called the cathode in this case, while all the negative particle, which is a chloride in this case, is now, of course, migrating and is being discharged at the positive rod, so as a chlorine gas, while the sodium ion will be discharged as sodium metal. And you know that a metal sticks on metal, so this metal sticks on most rod anyway, so because of the adhesion there, so this sodium is going to be sticking on the rod as normal Na, not as Na plus this time around. It comes out of the solution and stick as the visible metal, you know. Okay, now electrovalent or ionic compounds. What are electrovalent compounds? Electrovalent or ionic compounds are compounds that ionize in water to form ion. They are normally good conductor of electricity, hence we say they are good electrolytes. Now, examples of electrovalent compound are sodium chloride, magnesium chloride, acid, and all the bases, you know. So all the acid, you know, and all the base, you know, so they are all electrolyte because they will conduct electricity. Yes, they will conduct electricity, so that is what it means, or because they all ionize in water. So I hope you know how to identify electrovalent compounds or ionic compounds. A compound made from a metal and a non-metal. Yes, and then all the acids, all the base, think of any acid, you know, H2SO4, base, you know, NaOH, so think of all the base, and then of course salt of ammonium is also an electrolyte. Okay, that's is it. Okay, covalent compound. What are covalent compounds? Covalent compounds are compounds whose bonds are formed by electron sharing. So they are generally gases, e.g. chlorine, methane, hydrogen, carbon dioxide, and then they are also generally volatile liquid, you know, H2O, ethanol, benzene, hydrogen chloride. So they are covalent compound. And then, of course, hydrogen chloride gas is different from hydrochloric acid. Take note of that. Hydrogen chloride gas is not the same thing as hydrochloric acid. I told you all acid are this thing. That's because when dissolved in water. So but in this gaseous form is a covalent compound. Now, of course, volatile solid like iodine. Please remember how to identify covalent compound. Compound consists combination of a non-metal, two non-metals, or more than one non-metal. You say yes, that is a covalent compound, all right, or a covalent substance. Okay, now electrovalent, electrolytes and non-electrolytes. When do you say a substance is an electrolyte? A substance is an electrolyte when it is capable of conducting electricity. When it's capable of conducting electricity when dissolved in water, which means it will break down into water as positive and negative particle, where the positive migrate to the cathode and the negative migrate to the anode. Examples of covalent, of course, non-electrolytes. Non-electrolytes are substances that will not conduct electricity. That is what it means. And so that means because they don't ionize in water, that's why they are non-electrolytes. So example of non-electrolytes are organic substances like urine, ethanol, benzene, sugarcane. They are normally non-electrolytes. Most organic substances don't conduct electricity. So apart from the acids, which are weak, electrolytes, so they don't normally conduct electricity. So take note of that. Then electrolytes, what are those electrolytes that we talked about? Electrolytes are one that will conduct electricity. That means that's because they can ionize in water, so we call them good conductors. So example of those electrolytes, I've mentioned those electrolytes for you. I said all acid, all base, and of course all acid, all base are electrolytes. And then salts, of course, salts that are soluble in water, they are also electrolytes. Of course, if a salt is soluble in water, it means it can ionize, break down in water. All right. Now, for example, we said if sodium hydroxide breaks down, it's of course sodium hydroxide, which is slightly soluble in water, and of course it's a weak electrolyte. It breaks down to give us Mg2 plus and OH minus. All right, that is what it is. Take note, group 2 hydroxide, normally from calcium and above, they are normally weak electrolytes. Okay, now let's move forward. Now, types of electrolytes. Now, I just gave you that, I just told you that there exists electrolyte and non-electrolyte. Now we are going to this electrolyte we're talking about are of two different types. We have the strong ones and the weak ones. The strong electrolyte and the weak electrolyte. Now let's talk about strong electrolyte. Strong electrolyte are those electrolytes that will ionize completely in water. That means if I'm dissolving a handful of that electrolyte in water, it means all the particles will dissolve in water, or when they are melted, all the particles will ionize, break down. It means all the particles will ionize. That means they will all break down into their individual ions. For example, if a handful of salt contains, let's say, just say for instance, if a handful of salt contains 10,000 particles of sodium, 10,000 molecules of that salt, all of them dissolves. Once all of them dissolves in water to ionize and break down to give ions, it means it's a strong electrolyte. Then examples of strong electrolyte are all strong acids. What are the strong acids we know? Hydrochloric acid is a strong acid. Hydrogen bromide, HNO3, H2SO4, these are strong acid. Then what about strong base? All the hydroxide of the group 1 are strong base. All the hydroxide of group 1 are strong base, as well as strontium in group 2. Strontium and barium and radium hydroxide are also strong. So, but from calcium and above, calcium hydroxide and above, they are weak. Okay, now, and all ionizable salts, all salts that are soluble in water, so they are also strong electrolytes. Then weak electrolytes, those ones that are partially dissolved in water. Examples of weak electrolytes are all the weak acids. What are the weak acids we know? Acetic acid, carbonic acid. We even have more. H2SO3 is not H2SO4. H2SO3 is hydrogen trisulfide 4 or trisulfide 4 acid is also weak, and then HNO2 is also a weak one. Then of course weak bases are ammonium, calcium hydroxide, even magnesium hydroxide, so forth and so on, and pyridine as well. Then let's talk about the electrochemical cell. Now, in the electrochemical cell is nothing but, of course, a cell that's where oxidation and reduction takes place. Now, for example, the good reducing agents, which are the strongly electropositive elements, are at the top of the series. So we are talking about the electrochemical series, please. Let's talk about the electrochemical series. Now, in the electrochemical series, the good reducing agents are at the top of the series. That means those that easily lose electron at the end of the day. That means those that easily get oxidized are at the top. Why the good oxidizing agents, which are the strongly negative elements, are at the bottom of the series. Remember, the reducing agents are the ones at the top, while the oxidizing agents are the ones at the bottom, which are those ones that normally accepts electron are the oxidizing agents, while those ones that normally donate electron are the good reducing agents. Okay, now this is an electrochemical series, so let's take it one after the other. So we have potassium, Of course, if you don't have what to remind you of this, you can use this. This is what I use in reminding myself of the electrochemical series, because this is what I have to apply in electrolysis. I just say, make a statement: lazy people still can't make Adams zealous in time. Let's hope copy mine some precious good. Mine some precious good. Where L there stands for lithium, even though lithium is in the electrochemical series, but we normally start from people, which is a potassium. So P as in potassium, then P as in potassium, then of course, and it has a symbol K, then S as in sodium, has a symbol Na, then C as in calcium, which has a symbol Ca, M as in magnesium, has the symbol Mg, then Adams as in aluminium, has the symbol Al, then zealous as in zinc, has the symbol Zn2+, then in as in ion, then T as in time, T as in tin, of course, then of course let's hope, that means let as in lead, then hope as in hydrogen, copy as in copper, mine as in mercury, some as in silver, precious as in, of course, there's platinum before gold. That is in the electrochemical series, so we are only focusing on the activity series. So of course there's platinum before gold. Anyway, there's platinum before gold. All right, so that is that. Now let me take this out. Now this down here shows what? Increasing discharge preference. Increasing discharge preference, which simply means that those at the bottom will easily be discharged. Those at the bottom will easily migrate. Those at the bottom will migrate better, will easily be discharged at the cathode. That means they will easily migrate to the cathode. That's for the electropositive series. Why those above, which are the very reactive ones, they don't easily get reduced at the cathode. So those that easily get reduced at the cathode are those below. Those are the ones that are not strongly electropositive. The ones that are weakly electropositive are the ones that easily get reduced. Then that is that. So then I told you that the ones that are weakly electropositive are the ones below, so they easily get reduced, or they migrate, they easily get reduced at the cathode. Then let's talk about the anion series. What I use reminding myself of the anion series, I just use this, and you can also use it. Oil in butter clothes, not still funny. Oil in butter clothes, not still funny, where the oil there represent OH, hydroxide ion, the in there represent iodide, the B there represent bromide, the Cl the rest chloride, then the N and NO3 nitrate, then sulfates, then the F there represent fluoride. Okay, now that's what it means. So oil in butter clothes, not still funny. Okay, now fluoride. Now which of them easily migrates? Of course, the negative ions migrates to the positive electrode, which is the anode. So what is the preferences in discharge? The preference of discharge is increasing preference discharge, means those above easily get discharge. That means at the anodes better than those below, which means if I have a solution of both hydroxide and any of these solution, let's say for example any of these solution at equal concentration, any solution containing chloride, bromide, iodide, it means hydroxide will be discharged preferentially. That's because it occupies the first position in the series, and that's because it is more electropositive than, of course, others. So the most electropositive ones for anions are the ones discharged, but for cations, the least electropositive ones are the ones discharged. I hope you have taken note of that concept already. So remember, those above are the least electronegative. That means they are the more electropositive ones. So which means they are easily discharged for anion. But for cation, the least electronegative, the electropositive ones, the least electropositive ones are the ones discharged. Okay, now we have gotten that concept, so we can now move to preferential discharge of ion during electrolysis. Now, cations with the lowest electropositive, that means those at the bottom are easily discharged preferentially, but anions, those at the top, yes, are easily discharged. Okay, factors that affect discharge preferences: one, the relative position in the electrochemical series. Like I told you, those above, those below for cations are easily discharged, but those above for anions are the ones that are easily discharged. So also concentration. So the one with the higher concentration might easily be discharged. So for example, even if it's at a relatively low position in the series, it means it can be discharged if the concentration is higher. Then if the ion has a higher concentration, then nature of the electrode. Some electrodes that have good affinity for some certain ion. For example, platinum is easily attracts chlorine to itself. So if platinum is easily attacked by chlorine, so the nature of the electrode also affects the discharge preferences as well. Now we have some assignments here. In an electrolytic cell, the negative electrode is called what? Of course, I told you what the negative electrode is called, and I said it's called the cathode. Then when an electric current is passed through a solution of molten brine, which ion will move towards the cathode? I've told you the ion that will move towards the cathode. It is the positive ion that moves towards the cathode. Give an example of a covalent compound that exists as a solid at room temperature. The only covalent compound that exists as a solid at room temperature is iodine. Then give two examples of a strong and weak electrolyte. I've said giving you all strong acids, H2SO4, or strong base, sodium hydroxide, potassium hydroxide, and then of course you do that. That's an assignment for you. Then list three factors that affect preferential discharge. We just said it now. One is the nature of, we said the concentration, the position in the activity series, and then the nature of the electrode. Now, which of the following cation possess the highest preferences to be discharged at the cathode in a solution of equal concentration? So, all these are cation, and I told you that the one that will discharge is the one at the bottom of the series, or the one that is relatively less in electropositivity. So the least electropositive, remember that this potassium occupies the first position. Then I think this also close before potassium, and then we have copper before gold. So gold will be discharged since it occupies the lowest position, and it is the most, among the four of them, it is the one with the highest, with the least electropositivity. Okay, which of the following cation is likely to discharge at the anode during electrolysis having the same concentration? So I told you that only those that are at the top of the series, which are those that are less electronegative, which means those that are more electropositive for anions are discharged. Okay, which is hydroxide. Then during the electrolysis of aqueous brine, why is chloride discharged, okay, and not OH? And that's simply because chloride, of course, if you look at it, in the series of aqueous brine, we have oil in butter clothes. Oil in butter clothes, not so funny. So we say oil OH in butter clothes, oil in butter clothes, not still funny. Now you see that OH occupied the highest position, but why is chloride, which occupied that fourth position, is discharged? That's because during the electrolysis of aqueous brine, they make use of a concentrated solution of this. So this one has higher concentration than OH and is very close to OH still. It occupies the fourth position fourth position, and which is close to the first position. Now remember that OH is of low concentration all the time, which is from water, which normally from water, low concentration. So because it has closeness to OH in the series and it's having a higher concentration, that is why it's discharged, whereas OH is very low but it's occupying the first position where it's very low. So that's why chlorine is normally discharged during the electrolysis. Then that is that. All right, if you like this video on ionic series, please ionic theory, please, I would like you to hit the subscribe button and like the page, and then please sit tight and for the next video on electrolysis, all right, thank you very much. I'll see you in my next video.